In this video, we're going to talk about measurements, that methodology used to quantify matter. When we take quantitative measurements, writing down numbers, that provides the information necessary for most hypotheses, theories, and eventually the laws. When we make a measurement, that measurement provides three different types of information. One is actually the number, so that's the value, which represents the size or magnitude of the measurement. Also, we need to have units on a measurement. For example, if I'm measuring the mass of something, is it in grams or is it in kilograms? I need to know the units. That allows us to compare units from one place to another, from one measurement to another measurement. And also, my measurement usually indicates some uncertainty in the measurement. In other words, a simple example would be the digits of a tool used. So if I look at this balance here, I can see it shows a certain number of digits. So let's look at those. Here I have the number. It reads out 190.7073. That's my number. Behind that, I always have to list the units. That's very, very important. List the units. In this case, this balance measures the mass in grams. It has 4 digits to the right of the decimal point. This last digit here is usually called its uncertainty. So we look at the last digit in the number that I reported, and that measures the uncertainty. So what units do chemists use? Chemists around the world have been using something called an updated version of the metric system. It is known as the International System of Units, or SI units, and it's been around since 1964. A group of people got together in 1964 and came up with this standardized way of measuring things. And as you can see, it's a French group that got together. So there are 7 fundamental units of measure in the SI system. One for mass, length, temperature, amount of a substance, time, electrical current, and luminosity. Those units are kilograms, meters, Kelvin, mole, seconds, amperes, and candela. In chemistry, we tend to think about the units of mass, the units of length, and the units of temperature. And we're also going to talk a lot about the units of moles once we get to a next chapter. Each of these has an abbreviation associated with it, which you need to know. So kg means kilograms, m means meter, K means Kelvin, MOL means mole, S is seconds, A is amperes, and CD is candelas. From those 7 fundamental units, we actually have some derived units. For example, area is a unit that we'd like to measure lots of times. It's just a combination of measuring the length several times. That's meters squared. Volume is just meters cubed. Density, which is a very important measurement that we do in chemistry all the time, it's actually a combination of 2 standard measurements, both mass and volume. So this is kilograms per meter cubed. We also have distance and speed, meters per second, velocity, etc. We do use pressure a lot in chemistry, and we typically measure that in pascals now. And we also have energy, and we measure that in joules. We used to measure that before 1964 here in the United States in calories. Some of these units, like for example kilograms per meter squared, are not convenient. Literally the scale is either too big or too small. So we also have some. This is just a list of the most common factors used to actually convert one measurement scale into another measurement scale. For example, if I come down here to milligrams, grams is actually part of a kilogram, but a milligram is 1/1000th of a gram. So I have this prefix out in front of it called milli. In chemistry, we often use kilo, that's a kilogram. Milli, that's a milligram. Micro, which is 10 to the minus 6, so that's 1/1,000,000th of a something. In this case, in this example, a micrometer is actually 10 to the minus 6th of a meter. Okay? And we have further ones. We have pico and femto. We have tera and giga. All these are used in chemistry. A lot of them that we're going to use this semester are going to be kilo. We're going to use centa, milli, and micro. Those are the big ones that we're going to be using. You need to understand that micro is 10 to the minus 6 conversion factor. Milli is 10 to the minus 3 conversion factor. Centa is 10 to the minus 2. And kilo is 10 to the positive 3 factor. Let's look at the units most often used in general chemistry to measure things like mass, volume, time, temperature, energy, and pressure. So 6 different things that we'll talk about in general chemistry. In mass, we use grams. We also use milligrams or kilograms. Volume, we use cubic centimeter, which is cm cubed or cc. We often use milliliters, liters, and microliters, and we need to interconvert between all of these. In time, we use seconds and milliseconds. In temperature, we use degrees Celsius, or we use Kelvin, and we'll discuss all these a little bit more as we move through the chapters. In energy, we use joules and kilojoules, and I've added in here kilocalories also because we just sometimes can't always use the SI units because we're stubborn in the United States, so we use kilocalories still. For pressure, we use pascals and kilopascals, and in America, we still use pounds per square inch sometimes in English units. Let's look at some of the equipment used in general chemistry to measure these 6 different measurements of matter. For mass, in chemistry, we use a balance. To measure volume, we use a combination of things. We use a Erlenmeyer flask, a beaker, a syringe, a graduated cylinder, a pipette, or even a more modern pipette that delivers a set amount of material. For time, we typically use an electronic timer. We typically never use a watch anymore, an analog watch. For temperature, we still often use a very simple thermometer, either alcohol-based or mercury-based, but we're now transitioning over to digital temperature measurement things using thermistor or thermocouples. For energy, we typically use something called a calorimeter, which we will do in the 2nd semester of general chemistry. And to measure pressure, we use a pressure gauge. We no longer use those mercury-based manometers where we look at the height of mercury in a tube. Let's look at some examples of measurement, and let's specifically look at measuring the mass and volume, essentially measuring matter because it's made up of mass and volume. The term we use for measuring mass and volume together is called density. The definition of density, represented here by D, is just taking the mass and dividing it by the volume. That is how we actually measure matter. In this case, let's do an example to show how we measure matter. Let's calculate the density, the D, of a water sample, which has a mass of 20 grams and a volume of 20 milliliters. So I take a measuring cylinder here, I put it on a balance, and I measure the mass. It gives me a digital value. I add some water to it, and I measure it right till I get to 20 milliliters on these scale on the cylinder. So I know I have 20 milliliters of water, and then I look at how much it weighs now. So I can calculate how much mass of water I put in there by taking 70 grams minus 50 grams to get 20 grams. So my volume is 20 milliliters of water. To do the calculation now, I know I have 20 grams divided by 20 milliliters. My density, my measure of the matter, is 1.0 grams per milliliter. Let's do another example where I want to measure the density of a piece of metal. I take this metal and I put it on a balance, and I see it has a mass of 51.842 grams. I take a graduated cylinder and I put some water into it, and I measure it. It's at 17.1 milliliters of water. I then take my chunk of metal and I put it in that graduated cylinder, and it displaces some of the water. So I take a measurement. It's 19.8. I take the difference of those two values and I find out how much water it's displaced, and that would be my volume. So in this case, I have 2.7 milliliters of water. So I can calculate the density by taking 51.842 divided by 2.70, and I get 19.2 grams per milliliter. Notice that in this table over here, I have the density of several different substances from a literature value. Notice that the units are either in grams per milliliter or grams per cubic centimeter. It turns out that I can convert milliliters to cubic centimeters, so they're the same thing. If I look down at this table and I look for a substance that has the same density, I look down here and I say, oh, 19.2 is very similar to 19.32. So this is probably gold, okay? And I know that there's always some uncertainty in my measurements, so it doesn't match the exact value in the literature. So density is defined as the amount of matter in a given amount of space. That's the quantitative physical property of matter, density. If I look at these quantities of density, so it tells me how much matter there is per space, and if there's a big enough difference in there, these compounds will actually separate. For example, if I look at this example here, I have water, copper, and mercury. So here I have water with a density of 0.998. I have copper with a density of 8.94. It weighs more for the same volume. And mercury, which has a density of 13.55. It's heavier for the same amount of volume. So mercury sort of sinks to the bottom. On top of that floats copper, and on top of that is my water. If I look over here at this graphic here, I can see water, which has a density of about 0.998 grams per milliliter. Copper's heavier, so it goes to the bottom. How about cork? Cork, I would suspect, has a lower density than water, and in fact, if I go to the literature, I find out that cork has a density of 0.55 grams per milliliter. It is actually less mass in a given space. It floats on top of water. Water typically is reported as having a density of 1.000 grams per milliliter. However, that's at 4 degrees. If I cool it down just a little bit, at 0 degrees, I actually have a less dense water. Now let's look at the temperature scales for actually measuring temperature. The most common temperature scale used in the United States is Fahrenheit. 212 degrees Fahrenheit is the boiling point of water. The average body temperature is 98.2 degrees Fahrenheit. The average room temperature is around 68 degrees Fahrenheit. And water freezes at around 32 degrees Fahrenheit. Fahrenheit is not used in chemistry at all anymore. In chemistry, we use Celsius and Kelvin, and degrees Celsius is most often used in the laboratory because it's a scale that is convenient. So the boiling point of water is 100 degrees Celsius or 373 Kelvin. The average body temperature is 37 degrees Celsius or 310 Kelvin. The average room temperature is 20 degrees Celsius or 293 Kelvin. And the freezing point of water is 0 Celsius or 273 Kelvin. When we make all these measurements, chemists like to keep data in a laboratory notebook. And typically we use tables, graphs, and charts to organize all that data. That organization actually helps us interpret the data. It also shows relationships. It presents that data to someone else so we can actually publish that data. So here is just an example of a laboratory notebook. Notice in this notebook I have a graph here. I also have some values, 100 milliliters each. I have some values that I've taken. These are just examples of a typical table that I would write in a chemistry notebook. I have a title and I have some headings above each column, which includes the units for that column. Here I have a line graph, or sometimes called a plot. In this case, I have an axis of mass and units of grams and the numbers. On the x-axis, I'm measuring volume, and I have units of milliliters, and here's all my data points. Okay. I also have a title to my graph. Often, scientists will actually report their data in bar graphs or in pie charts, but this is not quite used as often in chemistry. We typically have tables and line graphs. So how good are these measurements?